I'm going to use this small session to demonstrate how to do an optimization design for a very simple structure, and then I will explore what's the possible procedures we are going to follow for the design within this course. So roughly what we are looking at is, I think the gray part is a wall, and then the white board is a deck. Actually, we have some supporting structures to support this deck. I can't see very clearly from this angle unless I'm lying on the ground. So the good part, I'm in a vertical so that we can lift things up around. And then during the lifting, I try to keep the ratio to 100%. So it's a full scale design. So that's the real representing the real lens. You can have a feel about it. Um, and then, so to do the optimization, the first thing we need to form a structure problem. So it forms with, like say, how this structure is supported, like the boundary condition. So at this edge will be fully fixed. And then where is the load? So the load will be transferred from the deck to this bracket. So we can find a critical load to consider to make it simple. So I think if we consider load will be applied on the top surface, so if we apply the load on the tip, it will create large displacement within this bracket, and then if we apply the load in the middle on the other end. So we will consider a load here as the critical load location. Um, Next thing, which is important, is uh, how we can find the design space. Sometimes we call design domain to host the optimal structure we are going to design. Um, so we can find it is through by identifying using a box structure like this one. So this make it transparent blue box. And then I'm going to like hold all the structure in. Actually, currently, if you want to just see what's the this structure will hold in the space, we can actually edit it. So we can make it smaller, roughly this one. And then we can host this. You can see the structure will host roughly this space. So if you look from there, align them accurately, and then you can get this, we call it width. So when in this course, due to the limited source and limited time available to us to do the design, I think the similar scenario will happen in future if your project have limited time and limited computational resources. You will consider is to convert it to a 2D structure. Um, 2D problem to do the optimization and then make it back to 3D. Let's see how we can do this. So for the difference between 2D and 3D is you can see for the original bracket is 3D because there will be all variations along X, Y, and also along the Z direction. We consider the vertical one is Y, this length direction is X, and then parallel to the wall will be the we call it thickness, so Z direction. So uh, one important concept I want to mention here is there's for the optimization design, there's a very important concept. You need to extend your design domain to all possible locations to hold your optimal structure. Like I think for this direction, we can extend a little bit to parallel with this. I don't want to extend more because that we will extend out, probably we will bump into it. The other thing is we can extend along Y direction up to, I think this wall, this floor up to there. Um, or if there's other things block your way, you need to consider that. Let's see if I want to extend it to the wall, and then I can do it something like this, and then I will make it here, so it should be extended to the wall roughly. So that's we call it the extended design domain. And then to make a structure simple, we will convert it to 3D to 2D. So I will explain what is a 2D. 2D is we only focus the design within this XY plane rather than the Z direction will be the same. I will give you one example. This is the design I get from my optimal uh, from the MATLAB code I shared on Canvas, which is the BSO2DC.m. So you can see there's no variation along the Z direction. So we call it 60 direction. So we will set the thickness exactly the same as the original blanket. Or sometimes you can set the thickness all the way to the total, we call it depth or thickness of the deck along the direction. That's possible, but for this example, we will stick to the, we use a 3 individual blanket. So we will optimize one of them. So hopefully the other 3 will be the same. So next, let's see how we can obtain this. From MATLAB code, we get a 2D image. That's our graph output. And later on, we use Abacus to form this 3D structure. And it's very simple, just extrude it, right? Okay, now let's move on.